Code generation is the final phase of the compilation process. The generator takes the optimized intermediate representation and the symbol table as input to produce an equivalent target program in assembly or machine code. This backend assumes the input is free of syntax and semantic errors. It relies on 3 address code, quadruples, or directed acyclic graphs, combined with the symbol table for precise type and address information. The output takes 3 primary forms: absolute machine code for immediate execution in fixed memory, relocatable machine code for later linking into object files, or assembly language. Assembly language is frequently chosen as the output target. It simplifies the generation process by providing symbolic names for memory addresses and hardware instructions. Beyond producing a valid program, the generator must select the most efficient instructions for each operation to minimize execution time. This comparison shows how the compiler translates platform-agnostic code into hardware instructions. Incrementing a variable can be handled with 3 separate instructions or a single optimized INC instruction. The difficulty of code generation is determined by the nature of the instruction set. The compiler must choose the specific sequence that reduces the cost of the operation. The primary constraint is the time required to access memory. Operations that stay within the CPU are significantly faster than those requiring external memory fetches. The optimized single instruction sequence reduces memory access time. It executes the logic using fewer instruction words, which speeds up program execution. Every architectural decision made by the generator focuses on minimizing these calculated costs to ensure the target program is efficient. To calculate efficiency, we use a machine model where memory is byte addressable and the CPU contains a set of general-purpose registers. The cost of an instruction is defined as 1 plus the cost of the addressing modes for both the source and the destination. CPU registers have an addressing cost of 0. Since they are located inside the processor, they do not require extra cycles to access. External memory locations and hard-coded literals carry an addressing cost of 1. These require an additional word in the instruction, increasing its length. Adding a literal to a register, such as add #5, R0, results in a cost of 2. This represents 1 for the instruction and 1 for the literal value. A memory-to-memory move, like MOV B, is the most expensive basic operation, with a total cost of 3. These costs are a direct reflection of instruction length. A higher cost indicates a longer instruction that takes more time to fetch and execute. To minimize total execution time, the compiler prioritizes register allocation and attempts to eliminate external memory references wherever possible. To manage this, the compiler must track the location of data across thousands of operations. It needs to know which variables are in which registers at any given moment. The compiler manages this through 2 synchronized ledgers called descriptors. The register descriptor tracks the current contents of each physical CPU register. The address descriptor tracks the location of each variable, noting if it is stored in a register, in memory, or both. These descriptors are updated after every instruction. This ensures the compiler has an accurate map of where every value is located before the next operation begins. This state tracking prevents the compiler from redundant memory calls and ensures that active data is not accidentally overwritten during the generation process. The decisions regarding where to store results are handled by a subroutine called getReg. Its primary function is to find the best location for the result of a computation. It always attempts to find an empty register first to avoid memory costs. If all registers are currently occupied, getReg must find a way to free one up for the current operation. This leads to spilling. The compiler stores a register's current value back into memory to make the register available for a new variable. Because spilling adds instructions and increases memory access, the getReg algorithm is designed to minimize this occurrence. We can see this in practice by generating code for the expression D equals A minus B plus A minus C plus A minus C. We'll track the descriptors through each step, starting with T equals A minus B. The compiler translates the first operation into 2 instructions. Variable A is moved into register 0, and B is subtracted from it. The register descriptor is updated to show that register 0 now contains the intermediate value T. The address descriptor marks register 0 as the valid location for T. By keeping T in the register, the compiler avoids the cost of writing this intermediate result back to memory. The second operation is U equals A minus C. Variable A is loaded into register 1, C is subtracted, and the descriptors update to show that U resides in register 1. For the operation V equals T plus U, the compiler simply adds register 1 to register 0. Both values are already in registers, so the instruction cost is minimal. The final operation, D equals V plus U, adds register 1 to register 0 again. Finally, the result in register 0 is moved to the memory address for D. The descriptors are updated to show D is now in both the register and memory. Through this sequence of register reuse, the compiler has successfully completed the calculation while minimizing the total instruction count. When viewed as a whole, code generation is the final output of the entire compilation pipeline. It follows parsing, which uses stacks to identify handles and reduce the input to the start symbol. It builds on syntax-directed translation, where synthesized and inherited attributes pass information between nodes in the parse tree. It also relies on the optimization phase, which reorders code, moves invariants out of loops, and reduces operational strength. All these preceding steps serve to provide the code generator with the most efficient logic possible for translation into hardware instructions. For students preparing for exams, mastery of this subject requires a clear understanding of the practical steps used in code generation. Always provide visual diagrams. Be prepared to draw parser stacks, directed acyclic graphs, or the flow of data through registers. When solving code generation problems, explicitly show the state of both the register and address descriptors after every single instruction. Ensure you can define the core mechanisms of the compiler, including spilling, ambiguity, and backpatching. Success in compiler design is found in the ability to track the flow of data through these constrained hardware systems accurately and logically.